Yes. So we were saying that we are going to use the Young modulus. Okay, we are going to use the Young modulus formula to calculate for our Young modulus in this case, because for this question, it is a load extension curve. Okay, and it is easy to calculate for, because even the 250 you are seeing over here, the 250 does not have a strain. Okay, but you can see that the 150 has a strain. So we can use this 150, which is the load. We know that our stress is equal to what? Let me say load over area. We've already calculated for the area over here. You see, so we are going to use the AO, the original area. Okay, because AO must go with what? AO. Uh-huh. The AO must go with the original stress that we are coming to calculate for. Okay. Uh-huh. So what are we going to do? What are we going to do in this case? We know that stress is equal to force over area. So this can also be written in a simplest form, known as this. Okay, that is the stress being expressed as what? P over A, force over the area. Okay, but in this case, it's not just any area, but AO. That is the original area. And then the strain, as we all know, it becomes the change in length over the original length. Okay, change in length over the original length. 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 Okay, so let me rewrite this well, and then we use this to solve our question by substitution method. Good, good, good. We are good to go. So this, finally, if that is what I'm saying, then it means that this can also be written as this, or let me say, Young modulus of elasticity can now be written as this. That is E is equal to P over AO. P over AO. Okay, let me put it into brackets as you are seeing, divided by change in length over the original length. Change in length over the original length. Since this is the problem we're having over here now, we can just do substitution and then we are good to go. The load, we say we are going to use 150 because it has an extension of 0.21, which is extension is known. The 150 load. Good. So we are going to now use in place of P, we are going to put that load over there. The area AO has already been calculated for. So we are going to be using this area exactly. What else are we supposed to do? What else are we supposed to do? The change in length. The change in length, we are going to use 0.21 as you are seeing over here. It has already been provided, making life easier. You have to be able to use a load whose extension is known. You cannot use any load whose extension is not known. Good students should jot this down somewhere. This is something you will not see anywhere. We say that to calculate for the Young modulus of a hot load extension curve, we are always supposed to use the load whose extension is known. The load whose extension is known. The load whose extension is known. Exactly. And also we said that the strain is equal to what? Change in length over original length. In this case, when our change in length is equal to 0.21. Okay. So the original length, which we already know, we are going to adapt it, which becomes the 200 millimeters, as we all saw in the given. And this is it over here, the 200 millimeters. 200 millimeters. Exactly. Exactly. So let's just do substitution, substitute it into the, and let's proceed to make life easier. Okay. So finally, this is going to become this. That is our E is now going to be equal to our E is now going to be equal to, let's say, the P. So I'm going to say 150 times 10 exponent 3. Always don't forget it, okay? Because of the kilo. So 150 times 10 exponent 3. So that is 150 times 10 exponent 3. Exactly. Exactly. And then the original area was 706.95. So let's put it down, 706.95 706.95. 706.95. 706.95. So we just cover it nicely as you are seeing over here. What else are we supposed to do? This one too, let's go and look for the brothers and sisters and substitute it into it nicely to make life much more easier. Over here, we say we want to adapt the 0.21. Okay, since that was what was given, because we are using 150 kilonewton load as you are seeing over here, we must also use the same extension corresponding to it. So we're going to use the 0.21. So that is 0.21 as you are seeing. Okay, all over the original length or the gauge length. We say the gauge length is the same as the hot original length, and then that was 200 as I showed you earlier. Take note of some of these things. 200 as I showed you earlier. Okay, from this stage it's just a matter of punching. Quickly punch this into your calculator and tell me the answer. Failure to add unit to your answer will cause you to be penalized. So please, let's all punch this, let's all punch this, let's all punch this together. Take your calculators and let's all punch this together. That is 150 times 10 exponent 3. 150 times 10 exponent 3 over 0. Or let me say 706.95. Okay. Quickly close the bracket, bring your division sign, open another bracket on the calculator, punch 0.21, divide it by 200. You can now close your bracket, feed, and you realize you are going to get 202075. Okay. 0.3135. Okay, exactly. So let's all write down. Let's all quickly put that down. So we are getting 2020 75.3135. Okay, exactly. Newton per millimeter squared. Newton per millimeter squared. Let me quickly write this too well and let's proceed. Let me quickly write this well and let's proceed. So this is the answer I had. Please, are we all getting the same answer? Are we all getting the same answer? Are we all getting the same answer? Hello?
Yes, sir.
Okay. Any question? Any question so far up to where we have gotten to? Is anyone having any question to ask before we proceed? All right, all right. So let's take the other question. Let's take the other question. So our question B says that we should calculate for the stress at elastic limit. The stress at elastic limit. What is the stress at elastic limit? Let's go back to our diagram. And this is the stress at elastic limit. That is the 250. Okay. That is the, so what is the formula for stress? We all know that our stress is equal to what? Load over area. But in this case, they are being specific. They say we should calculate for the stress at elastic limit. The stress at elastic. So you are supposed to use load at elastic limit over the original length, or let me say the gauge length. Exactly. 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 So let's proceed. So this is our B. This is our B. And this is the load at elastic limit. The load at elastic limit. Load at elastic limit. Load at elastic limit. Exactly. No, we are rather supposed to calculate for the stress at elastic limit. So you're going to use load over elastic limit all over the gauge length. Good, good. So from here, our stress at elastic limit, okay, that is our stress. I can put, if I write subscript E, you should just know I mean the stress at elastic limit, okay, it's equal to load at elastic limit. So let me say the P at E all over the original area, okay, all over the original area. So I'm going to write AO. Don't get confused. Don't get confused. Okay. From this idea, let's transfer this same idea to solve our question. So from the knowledge we have just acquired, our stress at elastic limit, we are going to use the load at elastic limit, and the load at elastic limit that was given was 250 kilonewton. We already know that kilo is equal to 10 exponent 3. Okay, so we're going to write times 10 exponent 3. Good. Newton, we bring the Newton all over the area. We had what? 706.95 millimeters. 706.95 millimeters. Quickly squared. So quickly, let's all point this together. Let's all point this together and let's see the answer we're going to get. That is 250 times 10 exponent 3 all over 706 all over 706.95. And we are going to get 353.632. So that is our final answer is now going to become our stress at elastic limit. Let me say our stress at elastic limit is now going to become what? 353.63, let's say 1.8. Okay, exactly.
So, sir, please, when you are calculating it, you just calculate the top, you not calculate the area.
Okay, maybe you just joined, so that is why. We calculated for the area a very long time ago, even when we began the question. Look at where we calculated the area. You see where we started calculating for the area. Always remember, for this kind of questions, always the area should be the first thing you analyze.
Okay,
Once you realize you are being given different diameters in the question pair, they give you diameter 130. They come and give you a different diameter 2.25. Then that should even trigger you to calculate for your hot original area,
area.
the area at failure. You realize? Uh-huh.
Yeah.
The area at failure, this area you are seeing over here, is the area that I used to calculate for the, let me say, percentage reduction. Okay, the percentage.
Okay.
Uh-huh. So take note of some of these things. Take note of
Okay.
these things.
Okay. Okay, sir.
All right, thank you, thank you too. So we are done calculating for our question B, and then our question C says that we should calculate for the maximum stress. It's just the same trend. Okay, so let's quickly do that together. Let's quickly do that together. So this is C, and then the maximum stress. What did we say the maximum stress can also be called? How did we say the maximum stress can also be called? Any volunteer?
Sir,
Yes, sir.
please ultimate stress.
Thank you very much. So the maximum stress can also be called the ultimate stress. Any creative person around, anyone to tell me something else? What is the other name for maximum stress or ultimate stress? What can it also be called? So the maximum stress can also be written as this case. It can also be written as if you see this somewhere, it also means the maximum stress. All right, so we can also call it the highest stress, okay, or the stress at apex. The stress at apex. Good. So let's proceed to calculate for our maximum. It's just the same trend. What is the formula for stress? Stress is equal to force over area. Okay. But in this case, we are being specific. Which force are we talking about? We're going to use the maximum force over the what? Original area. Uh-huh. So our maximum stress, the symbol of stress as result, MAX, okay, is equal to our load. So that is the P load at what? Maximum point all over what? The area, not just any area, but the original area. I'm being specific. You see what I'm writing? So finally, our maximum stress, finally, our maximum stress, finally, our maximum stress is now going to be equal to, let's go back to our diagram. It's like, let's go back to the diagram, okay? So if these are maximum points, these are last, this 150 is in the straight line, okay? So in this region, stress is directly proportional to strain. We said that in the elastic limit, even when the load is being removed, the material turns back to what? Resume its initial position. Exactly. Exactly. So our maximum load we are using is 380 kilonewton, as you are seeing over here. That was the maximum load because look at it. This is a load extension curve. So the maximum load was 380 kilonewton. Don't forget to add a kilonewton. Don't forget to add a kilonewton. So you are going to write what? 380. 380.
Kilonewton.
So in now the kilo becomes the 10 exponent 3, the language of engineering. If you don't know what kilo means, you are in trouble. Kilonewton. Newton is just the unit of force. So anywhere you see Newton, you should know that Newton is a force. Newton was a scientist who discovered force. He was sitting under an apple tree one day. The apple just fell down. He started to ask himself so many questions. As a scientist, you are supposed to be curious. As an engineer, you should ask yourself more questions. Today we are in the world of AI. You should what? Get busy with AI. Ask AI more questions. Any question that comes in your mind, ask AI. Do you understand me? To make you to be more technical and make you to become the best version of yourself. Make AI your friend. Ask AI more. Learn more from AI. In the world of AI, you are not supposed to be the same. Do you understand me? Exactly. So let's proceed. Let's proceed. Our original area we calculated for was what? 706.95. This is it. 706.95. So that is the 706.95. Okay, millimeter squared. Millimeter squared. So let's quickly punch this on a calculator. Everybody punch this on a calculator and tell me the answer. I want to write them down. What are you getting? 380 times 10 exponent 3. All over 706.95 millimeter squared. What are you going to get? What are we going to get? You're going to
537.52.
Thank you very much. That was a wonderful contribution. We are going to get 537.52. We can just write at least 4 decimal places, okay? 0.3. Now we say Newton per millimeter squared. What is our next question? Our next question says we should calculate for the percentage elongation. Look at it over here. Percentage elongation. So we are going to calculate for the percentage elongation. So that is our question E, right? So that is our percentage elongation. Let me bring it over here. E. That becomes the percentage elongation. The percentage elongation. The percentage. That is the total extension, okay, over the gauge length times 100. and the percentage elongation. What is the meaning of elongation? What is the other name for elongation? What is the other name for elongation?
Extension.
All right. Which other name can you also give to elongation? So our
Deformation.
exactly. What other name can you give to elongation or deformation? So our percentage elongation, anywhere you see this is a symbol for elongation, percentage, okay. So our percentage elongation. So let me write it over here, our percentage elongation. I told you that elongation can be known as displacement, okay, change in length, extension, and many more. You should do well to know them. They change colors each and every time. You can meet them in a question, and if you don't know that this is the particular person who has just changed color into something else, you may face challenges. That's why you're supposed to know all the meanings and all the types in which it may be put to ask you. Do you understand me? Exactly. Uh-huh. So our percentage elongation, which we all know the formula is equal to what? The total increase in length, or let me say the total extension. Okay. So I'm going to put that over here as simple as that. Let me write it as this. This is the total change in length. That is the total change in length. Okay. We have so many type of change. If let me say like the T was not there, then you realize that it's just a what? A change in length and not much. But once you see the T beneath it, it becomes a what? A total change in length. Okay, good. All over the gauge length. Okay, all over the original length. Okay, times all over the original length times 100 times 100 times 100. So times 100. Let's all point this on a calculator quick. And let's go. So at the end of the day, what are we going to get? Our total extension on the graph was what? We are using the graph to solve the question. It was 60 millimeters. You see. So let me put the 60 millimeters down. This is it, 60. 60 over 60 millimeters. All over what? The gauge length was 200. 200 millimeters. So you see that millimeters will cancel millimeters times 100 expressed as a percentage. So let's do it together. Let's say punch your division sign on your calculator, 60, bring your cursor down over 200, cursor right times 100. What are you going to get? You realize that we're going to get 30%.
30%.
And since the question, you are supposed to leave your answer in a percentage form. You are being asked the question in a percentage form. So we say that therefore our percentage elongation is equal to what? 30%. Mhm. And that is our what? Our percentage elongation. Percentage elongation. Elongation. So let's just do what to calculate for the last one, which is the what? Uh, percentage reduction in area. Percentage reduction in area. So that become our question. Let me see. That become our question. Let's go to our question. So that become our question E. E rather. Okay. That becomes our question E. So if this is D, then that is going to become E. Uh-huh. So if this is D, then that is going to become our E. So let's go and solve our question E. Let's solve for our question E. So for the question E, it is telling us to calculate for the percentage decrease in area. So let me just put that down. Or better still, I could put this over here and write it. Percentage decrease in area. That is the percentage decrease in area. Percentage decrease in area. All right. So that become our percentage decrease in area. So after writing and putting down percentage decrease in area, we are just supposed to move on to calculate for it as simple as that, as simple as that. Exactly. So let's proceed. So the formula for our percentage decrease in area, the formula for our percentage decrease in area, as we were all saying, is the original area minus the area at fracture, okay, all over the original area times expressed as a percentage, okay. So this is it, our percentage decrease in area. So that is our percentage decrease in area, our percentage decrease in area, our percentage decrease in area is equal to our AO, our AO minus the A1 minus the A1 all over the AO. Always remember to put these people in brackets. Exactly. Expressed as a percentage times 100. So let's all do this together and let's see the answer you're going to get. Okay, times 100 times 100. Okay, this still remains. Let's all point this together. We calculated for the area somewhere, and this was 706.95, 706.95. Okay, let's go to page 2 and we will see it over there. This is this area. Okay, what is the A1? A1 was which A1 was 397.659. Okay, 397.6 397.659. So let's come and write it over there by substitution. Wherever we see that, that is what we are going to put over there. So our AO, since we already know the AO, we still repeat it for that. That is 706.95. Okay, then we bring over here minus. Now our A1 is going to come. Okay, that is the area at fracture. So as we said, it was 397. We adopted 0.659. Okay, 0.659 times 100. Okay, so let's all point this together. Quickly point this together and tell me the answer. Let's all point this together. So 706.95 minus 397.659. Okay, close the bracket. Bring your cursor down. 706.95. You can shift the cursor to the right side. Everyone, I'm done punching mine. What are you getting?
43.75.
Exactly. Exactly. So that is the answer we should all be getting. That is our percentage reduction in area should be equal to 43.75%. You are supposed to add your unit. It's okay. If you don't add a unit, you may be penalized. You will be penalized. Okay. Uh-huh. So we are done solving our question 1, and these are the answers we are getting. These are the answers we are getting. This is very, very flexible. This is very, very flexible. Okay. Uh-huh. That is the road to A and then from B to C is the same as moving directly from A to C. Okay. The road from A to B and then from B to C is the same as moving directly from what? A to C. Okay. Uh-huh. So let's quickly go and have a look at our second question. Okay. First of all, let me just talk a little bit about the given one last more time and before we even go to see our problem 2.2. Okay. Uh-huh. The given, as we were told, the diameter was 3 centimeters. We have to convert it to 30 millimeters. The L was our gauge length, which we all know. The extension of load at 150 kilonewton is equal to 0.21 was in the what? Was in the straight line, okay? And in that straight line, Hooke's law was occurring over there, as we all said. The M, or let me say the maximum load, is also known as the ultimate load. That is the highest load, which we use to calculate for the what? The maximum stress. And also the total extension, okay, was the elongation that took place, was the highest form of elongation or that took place when the material went to what? Fracture. Okay, when the material went to failure. And the diameter of the rod at failure was 22.5 millimeters. Just imagine the thing being what? Let me say 3 centimeters, and now it becomes 2.25 centimeters. That is a very serious issue. We took our AO as our original area of the rod, and then our A1 as the area of the rod at failure. Yes, the area of the rod at failure. So let's come to our question 2. Let's analyze that together and see how best we can be able to wrap up with that question. Exactly. This question is saying that anyone to read the question for us before we proceed. Hello.
Hi.
Yeah, please, is there anyone here to read a question for us before we proceed?
Okay, I'm reading.
Okay, I'm listening.
A specimen of steel 25 millimeters in diameter with a gauge length of 200 millimeter is tested to destruction. It has an extension of 0.16 millimeter under a load of 80 kilonewton, and the load at elastic limit is 160 kilonewton. Take load at yield point to be 180 kilonewton and the maximum load in 180 kilonewton.
Okay.
The
Uh, After much, thank you very much. After much observation, I've decided to solve a past question as a last question. Okay. This one, since the solution are in your notes, you can relate it to understand. Okay. But rather, let's also solve something that you don't have a solution to. What I told you to go and find answers to. This is it. Okay. In the trial question, do all to find a solution and bring to me for marking. It's very serious. So if you meet it somewhere in future, don't blame me. Very, very, very serious. Take this serious. These trial questions, take them very, very serious. So let's solve for this question now. I'm just going to convert the given into a diagram. Okay. So we are going to solve trial question. I'm going to write question 2.1. Okay. Quick. Let's just use about 30 minutes to just finish it up and then let's proceed. So this is our question 2.1. Okay. That is a trial question. So take the trial questions very, very serious. Do all to solve most of them and send to me for marking. So this is our question. Let's say 2.1. So this is question 2.1. Okay. Let me quickly underline it nicely and let's proceed. Okay. Okay. So in this one, let's even start straight from our given. I said that we just want to convert the given into a what? A diagram. Quick, and then we proceed. Okay, for learning purposes. So this is my given. This is my given. This is my given. Okay. So let's start drawing the diagram from the question. Since we know that it is a load extension curve, let's put down the diagram over here nicely. Let's put down the diagram over here nicely for the given. So can be our origin. We can write over here. Okay, let's go to the question. Now the question is saying that a specimen of steel 20 a specimen of steel 20 diameter with a gauge length of 200 So let's just quickly pull that down. The specimen of steel has a diameter. So the diameter D is equal to what? 20 millimeters. 20 millimeters. 20 millimeters, and then the gauge length was given as what? 200 millimeters. Exactly. This was a very straight one. It's tested to distraction. It has an extension of 0.25 under a load of 180 kilonewton. So an extension of 0.25. You see, first of all, let's even draw the nature of the graph. Okay, so the nature of the graph, as we all know, always looks something like this. Since that is this was still, you see, before maybe it finally comes to fracture. So the 0.25 is surely going to be in the hot straight line. So that is 0.25. So we say 0.25. 0.25. Okay. This is our load. I write kilonewton. So this is our load. This is our load. So I'm going to write what? Into brackets kilonewton. If you don't see me writing kilonewton again, it's because I've already written it over here. It's because I've already written it over here. It's because I have already written it over there. Okay. So let me put the extension to also over here. This will become our extension. So the extension as it is over here, millimeters. Okay. It is over here, millimeters. So good, nicely. So our question, as our question was saying, let's proceed. It has an extension of 0.25 millimeters under a load of what? 80 kilonewton. So the load was 80 kilonewton. Let's put the 80 down. So this was 80 kilonewton. 80 kilonewton. And the load at elastic limit is 102 kilonewton. So the load at elastic limit. So let's say 102. 102. Okay. So the load at elastic limit, you realize that it doesn't have any extension. Let's go back to our question. And the load at elastic limit is 102 kilonewton. The reason why I wrote the 80 down is that you realize that surely the 102 is going to be bigger than the 80. So the smaller one will always come down, and then the bigger one will be going up as we are going up. Okay, so don't get confused. As you are saying it logically, to realize that 80 will surely come before the hot 102 because the thing is increasing, it's not decreasing. 0, 80, 102, you are going like that. Okay. So the maximum load is 130 kilonewton. And then the maximum load, let me calibrate it somewhere here. So 130,